Hello everyone, this is part 2 of section 2.1. We were verifying solutions, then using the principle of superposition to form a general solution, and then the initial conditions to find the particular solution. So one last example here, and we'll first verify. So for y1, which is e to the negative 3x times the cosine of 2x, we'll need two derivatives to verify. And the first derivative, by the product rule, first factor, derivative of the second is minus sine of 2x times 2, so let's write minus 2 e to the negative 3x sine of 2x, and then plus the second factor, cosine of 2x times the derivative of the first, and that's e to the negative 3x times negative 3. So let's make this a negative 3 e to the negative 3x times the cosine of 2x. And what I'm going to do here is factor out an e to the negative 3x, and we'll have negative 2 sine of 2x time, and then minus 3 cosine of 2x. So the reason for doing that is so we don't have to do the product rule twice. We only have to do the product rule once. So then for the second derivative, we've got the first factor, e to the negative 3x, derivative of the second, derivative of sine is cosine 2x times 2, so that makes this negative 4 cosine of 2x, and then the derivative of negative 3 cosine 2x, cosine becomes negative sine of 2x times 2, that's that positive 6 sine of 2x. And then it would be plus the second factor, what's in parentheses, derivative of the first is e to the negative 3x times negative 3. So let's write negative 3 e to the negative 3x, and then times the negative 2 sine of 2x minus 3 cosine of 2x. And to make things simpler, let's distribute and maybe collect like terms here for y double prime. So we've got negative 4 e to the negative 3x cosine 2x plus 6 e to the negative 3x sine of 2x plus 6 e to the negative 3x sine of 2x, and then it looks like plus 9 e to the negative 3x cosine 2x. So finally, combining like terms, we get, let's see, there's 9 and negative 4 is 5 e to the negative 3x cosine 2x, and looks like 12 e to the negative 3x sine of 2x. So verification kind of tedious here, but our substitution, okay, I'm not going to rewrite the equation, it's y double prime, so what we just found, 5 e to the negative 3x cosine 2x plus 12 e to the negative 3x sine of 2x, and then plus 6 times y prime. And for y prime, let's use the unfactored form, negative 2 e to the negative 3x sine of 2x minus 3 e to the negative 3x cosine 2x, and finally plus 13 times the function y, which was e to the negative 3x cosine of 2x, is that equal to 0? Let's just do this mentally. Let's focus on the cosines. Got 5 here. That makes negative 18, so 5 and negative 18 is negative 13. And the negative 13 cancels with the positive 13. And then we've got 12e to the negative 3x sine of 2x. Here's a negative 12. And those zero each other out as well. So, all that work, finally we get 0 equals 0. So it's verified. So, now the principle of superposition. So the verification is sometimes tedious. On an exam, I probably won't ask you to do that. And I would probably just tell you to find the particular solution. So by the principle of superposition, C1y is C1y1 plus C2y2. So C1, oh, and you could verify y2 on your own if you like. It's going to be the same routine for e to the negative 3x sine of 2x. Okay, so C1y1 was e to the negative 3x cosine 2x, and then plus C2y2 e to the negative 3x sine of 2x. And for this as well, it would be advantageous to factor out, because what we're going to do is use the two initial conditions, which are the function and its first derivative. So we need a first derivative for this general solution. And if you want, instead of doing two product rules, once again, we can factor out the e to the negative 3x. So C1 cosine 2x plus C2 sine of 2x. Now use the product rule on that to find the first derivative. And so we get the first factor, e to the negative 3x, derivative of the second, what's in parentheses. Cosine becomes minus sine of 2x times 2, so minus 2c1 sine of 2x, and then plus the derivative of sine of 2x is cosine 2x times 2, so plus 2c2 cosine 2x. Alright, big plus for the product rule. Second factor, what's in parentheses, derivative of the first is e to the negative 3x times negative 3. So I guess I'll change this plus to a minus 3 e to the negative 3x, and then times what's in parentheses. Alright, so we'll leave it at that and we'll go to the initial conditions. Because remember, with sines and cosines, things unfold neatly, because when we evaluated 0, for example, y of 0 is 2 is our first initial condition. Sine of 0 is 0 and cosine of 0 is 1. So into y prime, let's go into the non-factored form. The cosine of 0 is 1, all the e's to the zeros are 1s, and the sine of 0 is 0, so immediately we get y, which by the initial condition is 2, is equal to c1. So that's immediate. So that was fortunate. And then for y prime of 0, that was given to be 0. So then substituting into y prime, we have 0 equals, okay, the e to the zeros are 1s again, and the sine of 0 is 0, so this term goes away, and cosine of 0 is 1, so we just have 2c2, and then again the e to the zeros are 1, cosine of 0 is 1, sine of 0 is 0, so we get a c1 here, but don't forget there's the negative 3 out in front. And so there's an equation with two unknowns, but fortunately we know c1, So 0 equals 2c2 minus 3 times c1, which is 2. So that's negative 6. Bringing it to the left is positive 6. And dividing by 2 is 3. So c2 is 3. So therefore, our particular solution, y is c1, which is 2. Going up here, e to the negative 3x cosine 2x, and then plus c2, which is 3, e to the negative 3x sine of 2x. And that is our particular solution. Okay, so now we look at some theory regarding linear independence. So we had talked about this earlier. We'll formally define two functions. And again, we often see this open interval I thing. Nothing to be majorly concerned about, but we call them linearly independent, provided neither is a constant multiple of the other. So, for example, cosine and sine are linearly independent because they're not. You can't express one as a multiple of the other. E to the negative 3x, e to the 4x, because the powers are different. We cannot express those as multiples of one another, so they're linearly independent. But here's an example which is linearly dependent, because inverse tangent of 2x and 5 inverse tangent of 2x is just a constant multiple of inverse tangent of 2x. So they're linearly dependent. Now when we talk about general solutions, we had mentioned earlier that when we have our standard second order homogeneous, okay, we're talking about homogeneous in particular here, differential equation, that we had rewritten by dividing by everything by a of x, so that the leading coefficient is 1, or the coefficient of y double prime is 1. That just makes this function of x that was the coefficient of y prime and the function of x that was the coefficient of y different functions of x. So that's why we changed to lowercase p of x and q of x respectively. We saw that by Theorem 2, it always has two linearly independent solutions. And our method for finding those solutions, as we saw, was to use the principle of superposition, and it depended on a system of equations involving the functions and their derivatives, because we had to use the two initial conditions as we saw in those previous examples. So first of all, recall determinants. The determinant of a, b, c, d is just take the product of a times d and then minus the product of b times c. So for example, in this what we call the 2 by 2 determinant, 3 times 9 is 27, and then minus 5 times 7 is 35, so that gives us negative 8. And that leads us to a definition of what we call the Wronskian. It's the determinant formed by taking the two functions in the first row and their respective derivatives underneath in the second row. And then you could see by the determinant calculation it would be fg prime and then minus f prime g. And we have a theorem regarding the Wronskians of solutions. So suppose y1 and y2 are two solutions to the homogeneous second order linear equation. We want them to be linearly independent. And there's another formality again. But if they're linearly dependent, the Wronskian is going to be 0, And if they're linearly independent, the Wronskian is not 0. And here's the reason why part A guarantees linearly dependent. Because if they are linearly dependent, as we saw to begin this discussion, we said that one function is a multiple of the other. So let's say if f and g are linearly dependent, then we could say that f is a constant multiple, let's call it k, times g, or vice versa. So then the Wronskian would be the function f, function g, which is k times, well, actually, let me do it this way. The function f, the function g, will literally use the definition for now. F prime and then g prime. So then that gives us that w is, okay, f is k times g, so we'd have kg and g. And then the derivatives, kg prime and g prime. Well, that would give us kg g prime for the diagonal product from the upper left to lower right, and then minus kg prime g, which is the same as kg g prime. And you can see that that's always going to be equal to 0, so we'll use the triple equality, meaning is always equal to. So that proves linear dependence when the Wronskian is 0. And then we come to Theorem 4 here, which are general solutions. And this is just kind of a subtle point. If two functions are linearly independent solutions to the homogeneous second-order linear differential equation, if y is any solution, then there exist constants such that y of x is c1y1 plus c2y2. So you're thinking it's saying the same thing that the superposition principle did, but it's implying that if we find two linearly independent solutions, then we have found all of the solutions. And we call y of x a general solution. Not the general solution, it's a general solution. Because, for example, it could easily be verified that e to the 3x and e to the negative 3x are solutions to this. Okay, I think we actually did an example 1. And you can calculate the Wronskian to prove that they're linearly independent. So y1 is e to the 3x, y2 e to the negative 3x, so their derivatives 3 to the 3x, negative 3 e to the negative 3x, and the Wronskian gives us negative 3 e to the 0, and then minus, because we're adding exponents, and then minus 3 e to the 0 again, because we're adding exponents, and 3x plus negative 3x is 0. So that's minus 3 times minus 3, which is minus 6, which is obviously not equal to 0, so therefore they are linearly independent. So we would say that a general solution is y equaling c1 e to the 3x plus c2 e to the negative 3x. And the reason we say it's a general solution is because they're linearly independent. We're saying we found all the solutions, but you might recall that the hyperbolic sign of, let's say, 3x is, by definition, e to the 3x minus e to the negative 3x over 2, and the hyperbolic cosine of 3x, by definition, is e to the 3x plus e to the negative 3x over 2, where these are just linear combinations of the general, so the previous e to the 3x, c1 e to the 3x, c2 e to the negative 3x. So you could also say that y equals c1 hyperbolic cosine of 3x plus c2 hyperbolic sine of 3x is also a general solution. So that's kind of a subtle point, nothing to really worry about. And we'll move on to the final page of our notes for section 2.1 here, and talk about special situation where we have linear second-order differential equations with constant coefficients. So recall that the second-order differential equation, homogeneous, was a of x y double prime plus b of x y prime plus c of x y, if it's homogeneous, is equal to 0. And if these are functions of x, we're saying a of x, b of x, and c of x all could be functions of x. But if they're constants, then that equation becomes ay double prime plus by prime plus cy equaling 0. Again, where lowercase a, b, c are constants. So the idea is that we're going to look for a single solution. And we're going to assume that e to the rx is a solution because of the fact that the derivative of e to the rx are just constant multiples of itself, so that if the y is e to the rx, then y prime is just going to be a constant multiple, r e to the rx, and y double prime r squared e to the rx. So let's show that in particular here. If we're assuming y equals e to the rx is a solution, we'll calculate two derivatives. Y prime would be e to the rx times r, or r e to the rx. Y double prime would be, the r is a constant multiple, so the derivative of e to the rx again, e to the rx times r, so r times r squared e to the rx. And then if we make a substitution into our linear second order differential equation with constant coefficients, we get a times y double prime, which is r squared e to the rx, plus b times y prime, which is r e to the rx, and then plus c times y, which is just e to the rx must be 0. And then if we factor out the e to the rx, we have ar squared plus br plus c. The e to the rx times that must be 0. And then we could divide out the e to the rx, because no matter what x is, e to the rx is never 0, and so we get ar squared plus br plus c equaling 0. And that's monumental. That equation is what we call the characteristic equation of the second order linear differential equation with constant coefficients. And so notice how it's just like we're replacing y double prime by the r squared, y prime by an r, y by really r to the 0, you could even think of it as, which is 1. So then we have a theorem for distinct real roots. And if the roots of our characteristic equation are real and distinct, then a general solution is c1 e to the r1x and c2 e to the r2x, where r1 and r2, as we mentioned here, are the distinct roots. So basically, when we now have a tool to be able to solve these second order linear differential equations with constant coefficients. We first form the characteristic equation, so I'll just say CE, and for this example would be r squared plus 2r minus 15 is 0, and then we're going to factor, because it's a quadratic, so it looks like an r and an r. Doesn't matter what order. Looks like if I put a plus 5 and a minus 3, it'll work. Set each factor to 0. So r plus 5 is 0. R minus 3 is 0. So r is negative 5 and r is 3. Note that those are two real distinct roots. And so therefore by our theorem, a general solution is y equaling c1 e to the negative 5x plus c2 e to the 3x. Okay, so now we know how to solve these types of differential equations. So as long as they have constant coefficients, characteristic equation first, in this case 2r squared plus 3r equaling 0. Okay, remember the first thing you look for when factoring is the greatest common factor. So in this case we have to factor out an r, and then we have the quantity 2r plus 3 is 0. Set each factor to 0 again, so r is 0, 2r plus 3 is 0, so 2r would be negative 3, and r negative 3 halves. And so then, by the theorem, a general solution is c1 e to the, I'll show it one time here, e to the 0x, and then plus c2 e to the negative 3 halves x. But what I was meaning when I said just show it one time, there's no need to show a substitution for when r is 0, because e to the 0, of course, is 1. So that's just going to be c1 plus c2 e to the negative 3 halves x. Okay, and then here's another one, just to remind you that you should recall how to factor. That's basically what this becomes. It's just a little exercise in how do you factor quadratics. So practice your factoring skills. First, the characteristic equation. This should factor into the product of two binomials. If it doesn't, quadratic formula. But this one actually factors neatly. If we put a 2r and a 2r, okay, they both have to be positive because everything's positive, and the only choice is a 1 and a 3. Doesn't matter what order. And you could check that the inner product is 2r, the outer product is 6r, which combines to give the 8r. So that's the correct factorization. So set each factor to 0, 2r plus 1 is 0, and 2r plus 3 is 0. So r is negative 1/2, and r is negative 3/2. And so then a general solution is y equaling c1 e to the negative 1/2x plus c2 e to the negative 3/2x. Okay, and then we have another theorem so that's for real distinct roots. And then we have another theorem for repeated roots. And so if the repeated roots are basically equal, the roots are equal roots. And if that's the case, then here's our general solution. C1 plus C2x is a quantity times e to the r1x, where r1 is that common root. And here's an outline of the proof. I didn't have enough room, and I didn't want to take up a new sheet of paper, so I kind of just outlined the proof here. If the roots are equal, then we basically have r equaling r1 twice. So it would mean that r minus r1 quantity squared would be the characteristic equation. And if we FOIL this out, we get r squared minus 2r1r plus r sub 1 squared equaling 0 as the characteristic equation. And consequently, this would be our corresponding differential equation, where the r squared is y prime, r is y prime, and we've got a y in there, really an r to 0, right? And you could easily verify that both of these functions are solutions to this characteristic equation. And they are linearly independent. So then by the principle of superposition, C1y1, C1 e to the r1x, plus C2y2, which is x e to the r1x, must also be a general solution. And we factored out the e to the r1x. So all you have to know, that's just, for the sake of proving it. But if you get two equal roots, this is a general solution. So in this example, we first form the characteristic equation. And it would be 9r squared minus 12r plus 4 is 0. This does factor as 3r, 3r, and both negative 2's. So setting each factor to 0, 3r minus 2 is 0, and 3r minus 2 is 0. So r is 2/3, and r is 2/3. So note that they are equal roots. So therefore the solution y is equal to c1 plus c2x times e to that common root, e to the 2/3 x in this case. Alright, so that's the end of section 2.1. So we'll see you when you're ready for section 2.2.